We'll move on to next talk by Professor Julia. She is very much here.
Yes, I am here. Thank you very much. I don't want to delay anything. I know that the time is running short. Thank you very much, Prasad, for everything that you are doing. It's highly, highly appreciated. This turned out to be a wonderful conference. And without any delay, I just want to give the word to the recording, and I will be here the whole time.
It is wonderful because you are all joining your hands and made it successful. Okay, thank you. Please.
Hello, everybody. My name is Julia Volaufova, and I feel extremely privileged and honored that I can take part in this festive celebration of Professor C.R. Rao's 100th birthday. Before I start the topic that you can see on my screen, I would like to share with you some personal memories that I have during my life and I cherish forever. So, of course, every statistical student came across the name of C.R. Rao either through textbooks or publications. It's an inevitable. And so my first encounters are from early 70s. However, I don't have with me the documentation of exchanges of letters that I had because they are somewhere back in Bratislava in Slovakia. So time went on, and then in 1994, I was honored to chair the organizing committee and the program committee of an international conference, Probastat, that took place near Bratislava in Slovakia in a beautiful castle called Smolenice. And so we had the opportunity to invite Professor Rao, and he was awarded an honorary doctorate. Awarded by Slovak Academy of Sciences. So here is a memory, a picture of that, and around CR, and of course me many years ago, there are the dignitaries of Slovak statistical life, the Dean of the School of Mathematics and Physics, Director of the Mathematical Institute of the Slovak Academy of Sciences, and so on. So the year 1994 was pretty interesting. So I just want to mention one thing, that we were, of course, it's a small country in the center of Europe, and CR and his wonderful wife Bargavi, they came, and I had an honor to host them, and it was amazing how well prepared they were, how big effort they put into the travel. They knew everything about the history of the country. They knew everything about the architecture. They knew more than any native. The names of architects and artists who created the beautiful fountains in the center of the city, and all that. It was just really very, very pleasant. So, as I mentioned, this year was pretty memorable, and it was the year that I came to US. So, as I arrived, shortly after that, CR invited me to Penn State, where he was at the faculty at the time, and I gave a talk. And so after my return, he sent me this note, which says, Julia, here are some pictures of you. We were happy and to be with you in State College and listen to your seminar talk. When you are ready to travel to India, please let me know, CR, which didn't happen so soon, but eventually it did. And so several years later, in year 2000, CR celebrated his 80th birthday, and it was the year of celebrations. There were several conferences arranged for on his honor, and so I had the chance, and I was very lucky to take part in two of those. One was in San Antonio, Texas, and one was in Hyderabad. And to be honest with you, I'm actually not quite sure where was this picture taken. I think it's in Hyderabad, and the following one, but both are from year 2000. So it's a very nice memory, and I will always remember that. And so during that time, those years, I was in Baton Rouge at the research center, and we had an opportunity also to invite CR to give a talk. And again, I was very lucky and privileged to be his host. And so we showed him around the city. Here, the background is not very pretty, but the people on the picture are pretty good. So it was either 2000 or 2001. Now I don't remember exactly, but I think it was still sometime during the year 2000. So that's so wonderful to have these pictures and the memories. And CR, if you are listening, if you are on that, I will be always your friend. So let's go back to my main topic, and let's start very simple. I wanted to put together something that is related to CRO's work, and so I pulled out the paper that we just recently published jointly with Lynn Lamotte and Simo Puntanen, and this is the excerpt of the results from that work. So let's start with a simple linear regression where we consider the y hat being the estimated mean of the response vector y in the model, which is usually denoted by a triplet y, x beta, sigma square identity, where x beta means the expectation and sigma square identity the covariance matrix of the n-dimensional random response y. The y hat is usually denoted by expressed by as the expression hy, where h, and here it has a subscript 0, which has its meaning for the future. It's called a hat matrix, and it's nothing else, just a projection matrix on the column space of the matrix X. And so in this setting, nu naught, let's denote it by nu naught, is the same as the rank of X and the trace of matrix H naught, and it's referred to as model degrees of freedom in this model 1. So that will play a role later. Notice that here we don't assume the full column rank of matrix X. So very often in this setting, the situation is that we would like to smooth the fit of the response on the in the linear regression, and so we want to impose penalties on the vector parameter beta in order to smooth the fit. Often the penalties, the restrictions are formulated as a system of linear restrictions given by a matrix D in such a way that D beta equals to 0. Of course, these restrictions are not met, and strictly speaking, and so there is usually a formulation of being close to the restrictions, and the penalization of the departure from the restrictions is usually given by a constant k, which is non-negative. Then in that restricted setting, we get the penalized least square estimate of x beta, which is given by yk tilde, and the k is honoring the constant k. Now here the matrix H with the subscript k is not a projection matrix anymore, but of course we can denote by nu k the trace of this matrix hk, and very often in the literature it's referred to as effective degrees of freedom. It's nothing new, it's around for many years. However, the properties of the matrix hk and nu k are sort of believe that they are known, but I have never seen an exact and precise proof of that. So what about those estimates? The estimates of the form yk tilde, they are referred to as shrinkage estimates because with k positive, the norm of the estimator is less than or equal to norm of the least squares estimator of the expectation. And so now what is in general believed, and you can find sporadically these statements without strict proof in multiple publications. For example, that if we consider this matrix, which is in the middle of the, right here in the hat matrix, then it's believed that with increasing k, the difference between the HK1, if K1 is less than K2, and HK2, and also in their squares, is a non-negative definite matrix in a way that it's some ordering happens there, and also that the new K, the effective degrees of freedom constant, is a decreasing function in K, and this is related to the first one, but it's for any K1 less than K2 that there is some shrinking happening. So this is for under the condition everywhere that we looked, the condition for the matrix X prime X plus K D prime D is that it's non-singular. So another minor comment here, that if D is an identity matrix, then we don't deal with anything else, just a well-known old ridge regression. And it's known that under this condition, as K goes to infinity, that the YK tilde converges to 0. So now let's, in the setting of the model that we are considering, let's assume that D is a matrix of second differences, which serves the purpose in smoothing. In that case, obviously, D is not a full column rank matrix. Also, it can happen, and it's more in recent times, it's a big hit. We can assume that the number of observations N is less than the number of parameters, that less than the number of columns on the matrix X. In that case, the matrix X prime X plus KD prime T may be singular, and it very frequently happens in applications that this matrix is singular. So what we do, we try and we manage to show the properties of the matrix HK and investigate the properties of the so-called effective degrees of freedom, the new K, in a very general setting. We show that they follow the well-believed properties under non-singularity of the matrix X prime plus KD prime D. And our condition is only and only that X is a non-zero matrix, nothing else. No conditions on relationship of the number of rows and columns or whatever, nothing else. So what we do, in this proof of those properties, we heavily rely on a theorem that is possible to find in the following quite popular textbook, which was published in 1971 by CR and co-authored by S.K. Mitra. I have to mention that this was actually my Bible when I got my master's degrees, and I had to go through that in great details, which was, I don't even want to say how many years ago. Okay, so here is a theorem that is slightly restated, that is from this book. And in the book, you can find it on page 121. And so in our setting, we try to a little bit to dissect this theorem and formulate it in more detail, but essentially it's the same. So what it says is that if we have two symmetric and binary matrices A and B, in addition, if we assume that B is non-negative definite, then let's denote by N the matrix whose column space generates the orthogonal complement of column space of matrix B, which is defined by the following expression. And so let's assume that, let's just denote that the rank of B is R, which is not even very essential right here. Then the statement is that if the column space of N transpose A is equal to the column space of N transpose AN, then there exists a non-singular matrix T such that both T prime AT and T prime BT are diagonal matrices. And conversely, if there exists a non-singular matrix T such that both T prime AT and T prime BT are diagonal, then the column spaces of N transpose A and N transpose AN are equal. Okay, so it's referred to as a reduction of the matrix. It's not strictly speaking diagonalization, because the diagonalization is defined by the inverse of the matrix. So, but it's a very, very useful theorem. So in our proof, we actually have we don't show it here, but in our proof we have detailed construction of the matrix T, which plays an important role. So it's an old theorem, as I said, from 71, and we found the use of it in our current setting. So let's go back to our situation. So we can show the following, that for any non-negative constant k, the first property is that hk is invariant with respect to the choice of the generalized inverse in the middle, which is obvious. It doesn't even have to be formulated in this proposition. Now the second is more interesting, that the column space of hk for any k is equal to the column space of x, no matter what x is. Just it's important that it's non-zero. So now let's move on, and let's just, for the sake of simplicity of notation, but without loss of generality, let's replace square root of k times d by d, just so that it's simpler. So from the previous two propositions, now we see that because x prime x and d prime d are not only that they are symmetric, but both are non-negative definite, hence the conditions of proposition 1 are met, that there exists a non-singular matrix T such that both T prime x t and T prime dt are diagonal. And let's denote them, the diagonal matrices, by capital delta 1 and delta 2. So 1 is always related to x prime x and 2 is related to D prime d. So obviously, the entries of the matrices delta 1 and delta 2 are all non-negative. And so now if we take the sum and denote it by capital delta, then it's very straightforward to show that T delta plus, where delta plus is a Morman-Penrose generalized inverse of delta, T prime is a generalized inverse of x prime x plus D prime d. And so that's very straightforward. So now from that, we see that the matrix H, where we drop the index K because it's absorbed in D, matrix X can be expressed in the following way. So let's do the following now. We have those two matrices, delta 1 and delta 2, which have non-negative entries on the diagonal, so either zeros or positive real numbers. And so let's rearrange the columns of matrix T in such a way that we group together the columns that correspond to the index sets in the following way. The plus pass relates to all those indices that both in delta 1 and delta 2, the corresponding element is positive. In the plus and zero, those obviously, right, that in delta 1 it's positive and in delta 2 0, and conversely with 0 plus and 0 0 when both are 0. Okay, it's very easy to verify that with non-zero matrix X, the index sets J plus plus and J plus 0 cannot be both empty simultaneously. And also, if D is a non-zero matrix, J plus plus and J 0 plus cannot be simultaneously empty. And of course, there are all other configurations that are possible, but these are just some observations that have some meaning for us. So now with these conventions, with this columns notation of the matrix T, we can see that the delta 1 matrix, the diagonal matrix T prime x t, we multiply it out by the partition matrix T, takes the form of the block diagonal matrices, where the off-diagonal blocks are all 0 because it's a diagonal matrix. And we see that the only non-zero blocks are the first two, because we are dealing with the matrix x prime x. And here in the partitioning of T, these are those entries which correspond to delta 1 0. And similarly, if we carry out this similar multiplication for D prime D, we get delta 2 having the following form, but only those are non-zero where the second subscript is plus. That corresponds to delta 2 positive. And from here, we see also something more useful, that these two blocks are zero diagonal matrices, and so from that immediately follows that xt0 plus and xt00 are both zero matrices. Similarly for the d plus 0 and the t00, the t plus 0 and the t00 are zero matrices. So from that follows that the null space of the matrix X is the column space of the matrix concatenated from T0 plus and T00, and similarly for the matrix D, the null space is the column space of these two matrices. So now we go back, because that was just such a middle step, and if we replace now the matrix D, but again back by square root of KD for K non-negative, then our excuse me, HK matrix takes the following form from the previous notation, as I already had it before, and we see that the constant K shows up only in these two blocks, and if we multiply out by xt and t prime x prime, the center of this, we see that we have a sum of two matrices in which K shows up only here because of the properties that we had right here. And so it's very easy to look at properties of the matrix HK. For example, if K tends to infinity, the limit of matrix HK, meaning element-wise, is the matrix which is right here, and which is nothing else, which is easy to show as the orthogonal projection matrix onto the column space of xt plus 0. Similarly, if we take the trace of HK, which is our new K, the effective degrees of freedom, from the expression on the previous slide, we see that it's a sum of two traces, where if we now investigate the behavior of new K with respect to K, for example, we take the derivative with respect to K, we see that it's a negative number, because here everything is non-negative, positive actually, in fact. Then from that we can conclude immediately that new K is a decreasing function of K, and that for K equal to 0, it's the rank of X. And if K converges to infinity, then the limit of new K is just the trace of this orthogonal projection matrix P plus 0. So recall that the rank of HK is for any K non-negative and any D, the rank of X. That's what we mentioned. That was actually in the proposition 2. So from that, it follows, we observe immediately that if new K is the trace of HK, that the trace has no relation to the rank of HK unless K is equal to 0. So moreover, we can show that if delta 2 plus plus is non-zero, this is the part of the diagonal matrix for which delta 1 and delta 2 both are positive, then it can be shown, it's not so complicated, that for K2 greater than K1, both non-negative, the differences of HK1 and HK2 and of HK1 square and HK2 square are non-zero and non-negative definite. So now let's go, this is now just the summary of observations for what follows from all this development, that let's consider back our restrictions on the vector parameter beta in the form of d beta equal to 0. So it's not complicated to show that in our notation that we developed, the column space of the matrix X t plus 0 is the same as the space of those X betas which meet the restriction d beta equals to 0. So now, if d prime t is non-singular, you see, then with k increasing to infinity, yk tilde shrinks to 0, right? Because the restriction is obviously, right? And so if that's not the case, if d prime is singular, then yk tilde shrinks monotonically toward pxc plus not y, which is nothing else as the least square estimate of x beta such that the restriction d beta equal to 0 is met. So there are some more of these observations that we can see that, for example, if X is not a full column rank, because recall we assume that X is only a non-zero matrix, but if the column space of D transpose is included in the column space of X transpose, that it can be seen that the index J0 plus is empty, and the matrix T consists only of these three partitions. On the other hand, if the column space of the transpose and column space of X prime have only a zero vector in common, then it can be shown that HK is for any K the orthogonal projection onto the column space of X. And in that case, YK tilde equals to Y hat no matter what K is. So more generally, it can be shown that HK is affected by the estimable part of D, the part of those of the column space of D transpose that it contained in X prime. So the final sentence, which I didn't even put here, is that the degrees of freedom are usually related to some properties of some like test, like chi-square or something. And so the term effective degrees of freedom is just a helper, but it has nothing to do with the dimension of the model space, as in the non-penalized situation. So that would be my talk, and here is a set of selected references, and the second one is the paper I mentioned that we just published recently. And so once again, happy centennial, CR, and many thanks for your attention. Thank you very much.
Thank you, Professor Julia. You have anything to say? Maybe you'll receive questions through mail.
Thank you. I will be happy to answer any emails if I get, because I'm worried about the time, but I'm here. So.
Thank you.